In this video I'm going to go through task 2 of Unit 1 materials for EDEXCEL physics. Apologies if after through this video another sort of pop-up comes up saying my video is ready for viewing. That's just the previous video for task 1 that's already finished converting. So I'm just trying to churn through these videos as quick as possible so that you guys can churn through them as quick as possible to make sure that you're making progress. So Part 2, task 2, is all about Hooke's law. So Hooke's law graphs, Hooke's law experiments, and how to calculate elastic strain energy from Hooke's law experiment. And although I didn't mention it in there, it's the idea of elastic strain in this Young's what am I about? The stiffness, sorry, the stiffness constant of springs or stretched substances as well. So that's what we're trying to link in here today. So we're talking about elastic energy and the stiffness from Hooke's law graphs and Hooke's law experiments. Okay, so straight on to the explaining everything, which is a very nice one. Okay, a very straightforward one. So the idea of stating Hooke's law, describe a Hooke's law experiment, and describe how to find the elastic strain energy. Okay, so Hooke's law. Force is proportional to extension. Okay, so remember later on when you're finding out the Young's modulus of devices, or Young's modulus, which you might not have covered yet, but when you do Young's modulus, it needs to obey Hooke's law for Young's modulus to be found from the gradient of a graph, of a stress strain graph. Okay, so Hooke's law is quite a key idea. It's the idea that force is directly proportional to extension. So remember, if something's directly proportional, if one doubles, the other doubles. So force, remember, can be figured out from mass, from m times g. Extension is just your length minus your original length. Okay, so it's in other words how much the length has changed. So on these graphs, okay, remember they could have mass, okay, but they should have force on the axes, okay, and over here they should have extension, but they might have length. Okay, so if we've got length, remember there will be a zero error. Okay, so if I just draw a pencil over here, okay, there'll be a zero error like this, and you'll need to account for that as the original length. That's fine. But if they did it as extension, there'd be a straight line through the origin like so. Now, key things to think about. The axis can be either way around, so be careful. Sometimes they have extension on this axis and force on this axis. It can be compression or extension. Both of those are ways of showing Hooke's law. As long as it's a straight line through the origin, it obeys Hooke's law. That's the idea of proportionality. The other way to check proportionality, so in other words over here, where they've drawn length and not original length, so let me just draw another one for that. Oh god, very poor axes there. I'll take a bit more time with this one. There we go. So you've got length on this axis and force on this axis. So we've got this weird idea of a zero error here because they haven't taken into account the original length. And they haven't measured extension. If you're trying to see whether something's proportional here, you need to take away this original length here, this value here, from all values. Okay, so checking for proportionality, what do you need to do? Well, as your y-axis doubles, your x-axis should double. That's how you check for proportionality. Don't just do it once. Do it twice, do it a third time. It won't be exact. You won't get exactly double. You get pretty close to it. So in terms of this data here, let's look at some values. So if I had 2, 4, 6, and 8, 10 and 12 as my forces, and that was 0.3, and that was 0.6, and that was 0.9, and that was 1.1, and that was hold on, what's 10 now? I'd say that was 1.5, and that was therefore 1.9, let's say. Okay, we can check for proportionality. Okay, so let's have a look at the first one. So 2 newtons, it's 0.3 meters. Okay, so at 4 we expect it to be 0.6. If this doubles, then this should double, and it does. Okay, so let's check another one now. Okay, 4, if that doubles, okay, we expect this to double. Yeah, it's about right. A bit off, not a problem. Okay, let's check another one. 6 doubles to 12. Okay, we expect to double again, one off, not a problem. You don't need to just check for doubling. You can check for trebling or quadrupling or whatevering. Okay, as long as you do consistent on both sides. So times that by 5. Okay, to get to 10. Times that by 5. Yeah, that's right. Okay, so it's directly proportional. Brilliant. That's how you check for direct proportionality. Now remember, if you're looking at it in terms of length, they'll include this idea of what the zero is. Okay, no, let's do like this instead. There we go. Okay, so we've got the idea here. There we go, of force and length. Okay, but this time we haven't got extension, so we want extension. So you've got to figure out how much is actually extending between each of these. So to do that, so I'll just move my camera over slightly. There we go. So to do that, we need to actually think about what's happening in each of these. Well, the zero force leads to this length. So that is your original length. So we don't really need that, but we need to use this value. How much is it actually extending? Well, that means it's extended 10 from its original length. That's extended 20 from its original length. That's extended 30 from its original length. That's extended 40 from its original length. So you can see that's directly proportional. However, if you tried it with length, it wouldn't be directly proportional. It would be directly proportional to extension. That's just me banging on a bit about direct proportionality and how to check for it. If you didn't get that, please play that part of the video back again so you get direct proportionality. It is key for the whole of year 12 and 13 physics to make sure you understand direct proportionality. So Hooke's law, done that. Describe a Hooke's law experiment. Okay, spring, mass on a mass hanger. Okay, ruler, measuring extension, done. Okay, in terms of safety, got to wear goggles in case the spring snaps. In terms of what you've got down here, you've got to have a retort stand and a clamp with a boss to hold the masses in place. Remember this, I put a string over here. I'm not sure why I put a string in there. It really shouldn't be in there. It should be stiffness. Oh, it's got stiffness later on. String is a mistake. Don't worry if you don't use the word string. So force and extension. Okay, force is what you're varying. Extension is what you're measuring. The spring is what you're actually extending itself. The length is what you measure. You need to take that away from the original length to figure out the extension. The stiffness of the string, the stiffness of the spring can be figured out. There you go. I said string. Okay, and that is due to the fact that force proportional to extension. You end up with this equation of F is equal to Kx. K is the stiffness. If you use y equals mx plus c, x being your x-axis, f being your y-axis, your gradient is therefore the stiffness. So from your graphs that you had before of force against extension, like these, the gradient of that will tell you the stiffness. The inverse of this gradient will tell you the stiffness. That's because it's force over force and extension the wrong way around. The area under that graph, so the area under this graph will tell you the energy stored, and the area on the other side of this graph tells you the energy stored there. So look at your axes is key. Okay, so if you didn't get that bit as well, play that part of the video back. So describe how electrical strain energy, describe how to find it out, area under the graph. Straightforward. Questions? Let's have a look. So task 2 questions, here we go. First one over here, line of best fit, straightforward because it's got a slight curve to it, doesn't always obey Hooke's law, only to a point. Okay, after that does not obey Hooke's law. Gone past this limit proportionality, no longer obeys Hooke's law. So you can see that they're just doing an experiment for Hooke's law in a slightly different way to the way we've done it. Essentially hanging the wire horizontally rather than vertically, but they've still got the idea of the mass acting vertically, so it works in exactly the same way. X on the limit proportionality, so you can see it's about over here somewhere. Okay. Calculate energy stored, again, area under the graph. You draw a line down, figure out the area under. Very straightforward. And remember the extension's in millimeters, sorry, so you've got to convert that into meters for the calculation. Raw property of the wire can be determined by calculating the gradient of this graph, so remember that's the stiffness. Explain how the graph would be different if they'd use a thicker piece of wire. Okay, so if there's a thicker piece of wire, you've got a larger cross-sectional area there, therefore it's like having 2 springs. If you had 2 springs, it's even stiffer now. Okay, so it'll be harder to extend, therefore the gradient will be larger. Okay, let's think about that that we've got over here. So larger stiffness, therefore steeper gradient. Steeper gradient, more force required. Limit proportionality at a larger force, okay, so the idea that it's stiffer. Cool. Got the idea of the area under the wire, or again you can use half fx, which is one of the equations on the equation list. Alright. So that's later on. There we go. Okay, it's common for pens to have retractable ink for refills. Okay, the force F is applied to the button at the end of the pen. The tip of the refill is pushed out of the body of the pen. This compresses a spring, so we're talking about compression here, not extension. Remember, Hooke's law can still apply. compresses the spring in the end of the pen so that if the button is pressed again, the refit is pushed back inside the pen. What sort of deformation must the spring undergo when compressed? So there's two types of deformation, elastic and plastic. If it's elastic, it goes back to its original size when the force is removed. If it's plastic, it stays deformed. Well, you don't want it to stay deformed, you want it to go back to its original size, okay, original shape. So the idea for that is you want it to be elastic so it returns to its original shape after the force is removed. It does not become deformed is the idea. So we've got some data here, force against compression. Again, we can check for proportionality there, so some quick check. We know how to do that now. Okay, so doubling, yep, doubling. Trebling from there to there, yeah, pretty much trebling. Okay, doubling from there to there, okay, yeah, doubling. Okay, 4 to 8 should be doubling, spot on doubling. Okay, so we know that we're going to get a straight line through the origin when we plot the data on this graph. Okay, look, they've got force on this axis, compression on this axis, and in millimeters. Okay, you need to convert that to meters for any calculations. And also, okay, the gradient will be on this side, so it's the inverse of the gradient, and any area unders will be on this side of the graph, not on this side of the graph like you used to, because of the fact they've got force and extension the other way around. Stiffness, you need to use the gradient for that. Force for certain millimeters. So once you've plotted your line of best fit, once you've plotted your graph and drawn your line of best fit, go across from 6, come down, see what force that is. Nice questions to get, very nice questions. Calculate the elastic energy stored in the spring at 6 millimeters. So you can use half Fx or half kx squared if you know that from the equation list as well, or you can do the area under from this side of the graph. Okay, pretty straightforward. Okay, the spring is replaced by another one with double the length but identical in all other ways. Okay, explain how the force required to compress this new spring by 6 millimeters compared with the force required for the original spring. Okay, so it's going to be harder to if it's twice as long. Okay, that's like adding another spring in series. That means it's easier to actually compress or extend it. Okay, so it's easier for this compression or extension to take place. So it's less force actually required to do all of this business. Okay, so let's double check this. So all of those yep, are exactly the same as what I was saying. Okay, exactly the same in terms of how to do it. Half kx squared, half of x you could have used, or energy under the graph, any of those. New force, half the original force. Okay, brilliant. So we're saying it's less because they're in series now. So it's like having one spring like this and adding another spring like this to it. So it's half the force actually required to do it. So to make it easier, you only need to compress each spring by half the original amount. So before it was one spring by 6, but by doubling the length, it's like adding 2 springs together. So each spring by 3, so that's half the force. Straightforward. Question number 7, which if I remember correctly is the last question. Oh no, that's that's it for task 2. Right, so task 2 is now complete. So next video will be going through task 3, which starts talking about stress and strain, if I remember correctly. Let's just have a look. Yep. So task 3 talks about stress and strain and how to calculate the Young's modulus of a material. Thank you for listening, guys, and see you next time.